Hello, everyone. Hope you're enjoying the Distributed SQL Summit by Yugabyte so far. So this is our next session. We'll be taking a peek behind the curtain. We'll be seeing how the read and write works in Yugabyte, and then also talking about some other concepts around that. Before we get started, a little bit about me. My name is Kashish Agarwal. I am working as a principal solution architect at Yugabyte. So I primarily work with our customers, helping them deploy their applications using Yugabyte in all of their environments and go live with production. I also help them with all of the deployment strategies and query and schema optimizations and the best practices on how to use Yugabyte. Everyone should know some of the basic concepts for Yugabyte on some terminologies that are used in Yugabyte database. Now, if you are an architect, you can focus on write and read path that will help you design the systems in a more resilient way and in a more optimized way. If you know how the data is flown with each write or read request in the Yugabyte database, you can figure out what would be the most optimal design for your database. If you're a developer, you can focus on how the data is actually stored on the disk, so you can choose the right data type and the right encoding for your data that needs to be stored on the disk. If you're a database admin, you can focus on how the data is actually compacted, what compaction is, and what are some of the parameters that you can use to fine-tune the compaction depending on the use case. There would be a live Q&A throughout the session, so feel free to just post your questions on the chat and we'll be here to answer those. So the first thing that we'll be talking about is mem stores. Now, mem stores are, as the name suggests, is memory stores or memory buffers that stores your data in the memory before that data is written onto the disk. So any write operation, which means your inserts, updates, and deletes, goes into the mem stores. For in Yugabyte, there's specific size in bytes. The default is 64 MB. However, this can be configured depending on the use case. Whenever a particular mem store is full, the system automatically marks this mem store as immutable, which means there cannot be any more changes to this mem store, and spins up a new mem store to start taking new writes coming from the application. Now, if you look at the diagram on the right, consider an application sending some put operations with some keys and some values. So let's say you have 4 animals, chipmunk, cat, raccoon, and dog, with some values that are just 1, 2, 3, 4. You can see how in memstore, those values are not in the same order coming from the application. So they are not in 1, 2, 3, and 4, but in the memstore, they are already sorted by the keys alphabetically. So memstore automatically sorts them when it is stored in the memory. Moving on, we have something called wall or write ahead logs. This is simply a copy of the memstore on the disk. This is needed in case there is a node failure or a power outage or anything happens to the memory. Then you need to have a copy on the disk just so that the data can be restored. Think of this more like an append-only file, which simply consists all of your write data one after the other. Now, if you look at the diagram, in this one, the order is maintained and it's all the entries are in the same order as the data is sent by the client. Moving on, we have something called flush. Flush is an operation that basically converts the immutable mem stores to disk. Now, we talked about mem stores and we talked about how those mem stores are, when they become full, they are marked as immutable. Every time that happens, there is a trigger that triggers the flush operation. And that flush operation converts this immutable mem table into something called a SST file. Now, each flush produces a single SST file for one mem table, and these produced SST files are also immutable, which means no changes can be performed on these SST files. Now, moving on, what are SST files? SST files is nothing but a copy of all of your data on the disk. We talked about walls, but wall is simply a copy of a mem store. But when a mem store is marked immutable, it's flushed into an SST, and at that time, the mem store and the corresponding walls are discarded. So you only have one copy of your data in SSTs after it has been flushed. Now, as your data set grows, you can have multiple SSTs, depending on how frequently you're writing. Now, this SSTs are divided are basically block-based files. So there are multiple blocks. We will look into all the blocks in detail further ahead in this presentation. But right now, this diagram just tells you how you have an index block, and then you can have multiple data blocks, and your data is organized into the blocks. And then an index block is basically a pointer to entries into the data blocks in order for the database to find specific entries. Now, these SST files are basically text-based files on the disk that can be compressed using certain compression algorithms such as Snappy and zlib. These SST files goes through compaction to better organize your data. We will look at what compactions are and how it is performed later down in the presentation. And we already talked about how these SST files are divided into multiple sections or multiple blocks. So these were some of the basic concepts. Now let's try to tie all of this together into a generic write path for YugabyteDB. So if you look at this diagram, consider this box on the left as your client or your application, where it has a smart driver installed to connect to Yugabyte database. Now, on the right-hand side, this entire big circle is your Yugabyte cluster, where each of these small circles are nodes for Yugabyte cluster. This circle in bold is just the leader node, and the two other are the follower node. RF equal 3 means replication factor of 3, which just means that your data would have 3 copies, and it would basically have one leader and 2 followers, which is what I just depicted in the diagram. So the first thing that happens is that the client driver sends a write request to the tablet leader node. So the driver has a partition aware policy. So it knows which node is the leader, and the write request is sent to the leader node. The leader, the very first thing it does is write that request into its own wall on the disk. So on the write ahead log, that entry is appended on the disk. As soon as that is done, the leader sends a replication request for that particular entry to the 2 follower nodes. So if you see 2B and 2C, it's basically done at the same time. As soon as the leader writes to its own write ahead log, it sends the same entry to the 2 followers. The 2 followers then write that entry in their write ahead log. And then as soon as they have completed the write request, they acknowledge the request back to the leader. The leader really is waiting for at least one of the followers to acknowledge. So in the event that you get 4A before 4B, or vice versa, you get 4B before 4A, the leader marks it as complete and just moves on to the next step. This also helps just in case this node goes down for some reason, you need ACK from at least one of the followers, and you can move on. As soon as the leader gets an acknowledgement from any one of the followers, it moves on to the next step and write that entry into its own mem store. And now that entry is in the memory of the leader as well. Whenever that is completed, the leader responds back to the client with a success message and basically says that request was fulfilled and the data is written. Now, on to the next. So on to the next write request to the leader. When the leader replicates that to the follower, that the last entry that was written just now is sent to the mem store. So the mem stores on the followers are not filled immediately because the followers, they don't know whether the last request was committed or not. So only when the leader sends a next request along with the payload, we send the status of the last request. And this is when the follower marks them as committed and marks the last entry into their mem stores. If there are no new requests, then at the next heartbeat, the leader sends an acknowledgement for the last request. And this is when it's stored in the mem store for the followers. So this is how a generic write path looks like for YugabyteDB. Let's move on and see how the read works in Yugabyte. So this is just a different representation of a Yugabyte database cluster. Consider you have 4 nodes, and out of the 4 nodes in the cluster, you have YB master process running on the 3 nodes. And then you have a T server process running on all 4 nodes of the cluster. The star over here denotes that this is the leader of the master process. And then the T server is simply responsible for storing your data and hosting also the YQL, which is the Yugabyte query layer onto that. Now imagine the user runs this very simple query where it's simply select from a table looking for a particular key. Now the first thing that happens is that request goes to a query layer on a specific node, depending on which node the client sent that request to. The query layer figures out, looking at the syntax and looking at what API was used, whether it's CQL, the Cassandra query language, or SQL, which is a Postgres compatible query language. Once it knows that what kind of query and it decodes the query, it sends that query to YB master asking for this particular key, which is in the where clause. The YB master, since it knows all the data distribution, it responds back by saying, hey, this particular key is, let's say, on tablet 2, right? And then the query layer sends that request to the leader of tablet 2, which is denoted by a star over here. Now, this is just a very broad example where I'm showing internode communication. The more optimized way of doing all of this would be having YB master and the query layer and the tablet on a single node, so you can avoid all of those network hops. But once the leader gets a request, then the leader looks for that particular key and the value that is being requested and respond back to the client. Now, when I say the leader looks for that particular key, the leader follows these steps. So the first step it does is to look for in the mem store, to look for that key. If that key is not found in the mem store, the leader starts by looking into the most recent SST file and then traverses backwards from there. Within the SST files, we already talked about how the data is stored within blocks in index as well as data blocks. So within the SST files, the tablet leader is looking for a particular index, and then based on the index, it knows which data block to look into, and then it does a linear search on that data block to find that key. So that was the read path. Now let's just move on and see how the data is actually stored on the disk. So consider this big block on the left as a table where all of your data is stored. Now in Yugabyte, this table is actually partitioned into multiple smaller tables, or which we call as tablets. Now, these tablets are are partitioned based on a partition key that is specified at the time of the creation of the table. Now, for each tablet, the data is stored into a wall, which we already discussed. As you're getting the write request, the data is stored in the wall and in the mem store. So you have a copy of your data on the disk. Now, when that mem store becomes full, a flush happens and creates SSD files, right? We already discussed that. So in addition to the wall, the data is stored into what we call as regular RocksDB database. And if you have transactional data, that data is stored into intent RocksDB database. So intent RocksDB database is nothing but a special instantiation of the regular database where we only store the data for a particular transaction until the transaction is committed. So think about when the application client starts begin transaction and then does a bunch of things inside that transaction. All of those write requests within a transaction is stored in intents database, and as soon as the application does end transaction, that transaction is committed and that data is moved over to regular RocksDB database. Now, regular RocksDB database is nothing but the different SSD files that we already discussed. So this is how the data is structured on the disk for each tablet. Now, we talked about how SSD files are divided into multiple blocks. So this is just assume that you have multiple SSD files, you have data blocks, and this is where your actual data resides for each of the SSD files. In addition to data blocks, you have multiple other blocks. You have a filter meta block, which holds your filter data. You have an index meta block, which is an index to all the entries in the data. You have compression meta block, which holds information about what kind of compression algorithm is being used on these SSD files. You have range deletion, some statistics, and some other metadata block on these SSD files. Now, moving on, your partitions can actually span multiple data blocks. Every time an entry is being read from these data blocks, that entire block is loaded into OS buffer cache, which is uncompressed, but it helps retrieving multiple similar values from the same partitions quickly. By default, SSDs are compressed using Snappy algorithm. Snappy is good. zlib can be better. It can compress by 20 to 30% more, but zlib algorithm is more CPU intensive. So depending on the use case, this can be configured and changed into zlib if use case requires that. This is how the data is stored physically on within each SSDs in the key value format. So everything that you see on the top is how the key is encoded on the SSD. On the bottom is the value. The key basically starts with a 16-bit unique hash to identify the key. The hash columns are the columns that you specify at the time of partition. When you created the table, you specify a partition key, and that is what the hash columns are. Range columns are any ranges that might be there. Your partition can comprise of one or more ranges. Column ID is the actual column ID which has a value associated. So for example, if you have a table with name, age, address, and telephone number, and you are just updating telephone number, the column ID of the column telephone number would be entered over here. Then this is the data type of that particular column. So for telephone number, the data type would be integer. So that would be right here. Physical and logical time of when that write request came in, and then a unique write ID that is assigned to each write request. So this is how the key is encoded. For the values, you have an optional time to live and associated with the actual value, which is the telephone number in our example. Moving on, let's talk a little bit about plushes. We talked about plushes in the beginning, but diving deep, each mem stores are tablet specific, right? And then they are allocated from a global pool of tablets. Now, there are two triggers that can trigger flush on these mem stores. If that global mem store size reaches 10% of the available memory, then the oldest mem store is flushed. And Yugabyte does that to avoid using a lot of your system's available memory. So we cap it at 10%. Or if a particular tablet mem store reaches 128 MB, this particular tablet is flush. Now this 128 MB is configurable. You can increase or decrease that threshold, but this is when that particular mem store is flushed. Every time a mem store is flushed, it's made immutable. A new one is allocated, skewed for the flush, and then flushed into an SSD files. If this mem store is queued, but let's say it's not flushed for whatever reason, and another one is ready, now you have two mem stores that are waiting to be flushed. And at that point, the system just stops accepting writes because we cannot just keep on ingesting data before we can flush the old ones. This is showed up as stalls in the metrics and can be controlled by a configuration flag where the default is 2, where we can only have two mem stores that are not flush. Now, for use cases that are very write heavy and you need more incoming data, you can tune this, and all of this can be configured depending on the use case. These are just the configuration flags that we just talked about. Memstore size MB is a size of the size of a memstore that can reach before it is queued flush. The default is 128 MB, can be changed. Global memstore size MB max is the limit of the combined memstores on for all the tablets on a T server. So on a particular T server, if combined memstore grows beyond 2 GB, then they're all flushed. Or we have a global memstore size percentage, which is the 10%. So if all the memstores combined take 10% or more of the system's available memory, then they are queued for flush. So that's how the data is actually stored on the disk. Moving on, let's see what compactions are and why do we need compaction to efficiently store the data. Now consider this example that we looked at in the beginning of our discussion today. You have some entries coming in from the client, and the client sent cat, chipmunk, dog, and raccoon with some values associated. But with time, the client is actually updating some values. So now cat value is changed to 5, chipmunk was deleted, raccoon's value was changed to 6, and a new entry for zebra was added. And then SST3 would have some more up-to-date values, right? Now, if you look at this, you have an entry for cat. You actually have multiple entries for cat in one in SST file 1, in 2, and in 3, but you actually care about the most recent up-to-date value for cat. You don't really care about the older values. You also don't care about the values that are already deleted. For example, chipmunk over here and raccoon over here. And if you think about it, the system is actually taking more space to store all of these out of date values. And also when it reads through these values, multiple SSD files, it's taking more time to find the most up to date value. And that is why we need compaction, where it compacts multiple SSD files into one SSD file, removes or garbage collects any of the deleted entries, and only keeps the most up-to-date entries uh, for the ones that are there. So this is on a very high level what compaction is, but let's dive deep into this. There are two checks before a compaction is triggered. The one is for space amplification, and the other one is for read amplification. So space amplification is 200% threshold. So anytime, when we check for space amplification and the threshold crosses 200%, we trigger a compaction. And it's calculated by this algorithm. So sum of size of all the SSD files divided by the size of the oldest SSD files. For read amplification, the threshold is 1.2, which is calculated by 100 plus this parameter, which is a configuration parameter, divided by 100. This configuration parameter is set to 20 by default, which can be changed. So if you change that, this threshold will change. And this decides when a compaction needs to occur. And once this threshold is set, this particular formula should be less than or equal to 1.2. Anytime it breaches 1.2, we trigger a compaction. Now, you don't need to memorize these formulas. We will do a short exercise right now, and we will see how these checks are actually taken into consideration before triggering a compaction. So before we actually trigger a compaction, consider this diagram, and each R is one SSD file. So you can have multiple SSD file. In this diagram, you have 12 of different sizes. Every time a flush happens, so mmstore is flushed into a SSD file. This is when it also kicks off the check to see whether we need a compaction. And the checks are what we just discussed. Each of those check will figure out and find the candidate sets for compaction. Now, for multiple SSD file or consecutive SSD files to be a candidate set, you need at least 4 SSD files of the same size. So R1, R2, R3, and R4 can be one candidate set, and these 5 files over here can be another candidate set. So now that we have identified a candidate set, let's say you have R1, R2, R3, R4, and R5 are 5 SSD files into considered as one candidate set, and assuming these are all 10 MB each. So every time a flush happens at 10 MB, and you are producing a SSD file of 10 MB. Now, the first check that the system would do would be for space amplification. So this would be sum of 4 files, which is 40, assuming they're all 10 MB each, divided by the last one, which is 10. This is definitely more than 200%. So this will trigger a compaction because it meets the space amplification trigger and gives you one big SSD file, which is of 50 MB. Now, as you're getting more writes, let's say you get more 10 MB files, and then this is another candidate set. The system checks for space amplification, and again, now your last 4 files are 40 and divided by the oldest one, which is 50. It's not 200%, so it does not meet the space amplification, and it then starts to get into details of the read amplification. It starts with R10 as the first candidate file divided by the size of R9. They are both equal, so the ratio is 1, which is less than 1.2, so it moves on. Then it takes these two, so 10 plus 10 is 20 divided by R8. 20 by 10 is 0.5, which is less than 1.2, so it moves on, and so on and so forth until it gets to the last one. And then whenever it crosses that 1.2 threshold, it does not include the next one, and see how many files we have, and then triggers a compaction. So those 4 files is compacted into R11, which is a 40 MB file, and then this one is 50 MB. And let's say you get more files. We do the same checks for space and read amplifications again. But then since we only have 3 files, it did not trigger a compaction. And then we are waiting for the 4th one. As soon as we get the 4th one, we trigger another compaction. Remember, I told we need at least 4 files to trigger a compaction. So this is how the compaction works. Now, to recap, we talked about some basic concepts to see what memstore, wall, flush, SST, and compaction means in YugabyteDB. We saw how the read and write path works for Yugabyte database, how the data is actually stored on the disk, and how that storage is optimized by using compaction so that we use less space and we can make reads faster. Now that you know all of this information, it can be useful for architects so they can design topologies based on read and write path by keeping how the data is flown. The developers can understand how the data is actually stored on the disk and can design their applications accordingly. The system admins or database admins can tune flush and compaction parameters and fine-tune the database depending on the use case. And all of us can just get the best out of Yugabyte database. So that's all for today. Thank you for joining me, and we'll take your questions on live. Thank you.